What's up, nerds? Today we're looking at projectile motion with air friction in Python. Projectile motion is probably one of the most basic thing in most first-year university courses. But there's a catch. It's not done with friction. Now, the nice thing about living in the modern world, of course, is we have access to resources like Python, where we can program and we could solve complicated differential equations that we can't normally do by hand on a computer. And while projectile motion is really basic for the case of no friction, it's just a parabola, it's unsolvable for when you have a frictional force. Today we'll solve for the trajectories of various objects that experience air friction, and we'll see what's the optimal launch angle to launch them at. With no air friction, as you know, the optimal angle is 45 degrees. The question, of course, is when you do have air friction, how does that change? And it turns out that it does. Now, only about half of you are subscribed to my channel, so be sure to hit that button below. There's a link to the Discord server as well in the description, so be sure to join that. There's lots of nice people there that have taught me a lot about various packages in Python that I actually use for some of my videos as well. Anyways, enjoy.
Greetings, class, and welcome to Physics 101. We got that classic topic, projectile motion. Gotta see how the cannonball goes, neglect how the wind blows. Air friction, what a joke.
But bro, your solution ain't even close. Solver here. Don't you listen to that guy at Friction Python piece of cake, bro. You barely even need to try. Take your ODE, put a dash of solve IVP. Got that solution looking fine. Easy.
So the packages aren't too complicated today. We have NumPy, of course, as always. Any analysis we do, we use NumPy, and SciPy is going to be used for solving the differential equation of the projectile motion. And then we're also going to use minimize because we're going to see for regular day objects like a soccer ball or a golf ball, what's the optimal angle that you send those to send them as far as possible. And of course, matplotlib for a little bit of plotting. So for an object moving under the force of gravity, when it's kicked, there's a net force on it, F net. And that's the gravitational force. And if you're just dealing with projectile motion with no friction, that's it. There's only the gravitational force that pulls it down. In this case, however, we have friction as well. And the friction force is given by minus b times the absolute value of velocity times the velocity. So what this is, if you think about this, if the velocity is pointing in a certain direction, this points in the exact opposite direction and pulls backwards. Gravity, however, is always pulling down. So you have this downward force plus this force that resists the direction of the motion. Noting that v is just x dot x hat plus y dot y hat. We're in two dimensions here. You can write the net force like this, so minus mg y hat minus b. So the absolute value of the velocity is just the square root of x dot squared plus y dot squared. That's pretty simple. And then the velocity itself is x dot x hat plus y dot y hat. So this is the vector here. Again, not too complicated. I like to put things in vector form because it makes it a bit more simple. So f net is writing it in terms of x and y components. We have our x component here, which is just from the friction, and the y component, gravity plus the friction. So of course, the most common law now is Newton's law. That's that F is equal to ma. So we've established what the force is, and now we can get our differential equation. That's what F equals ma technically is. It's a differential equation. So we have F equals ma is m x dot dot, acceleration in x, acceleration in y. And we set this equal to the net force here, and that gives us our differential equation of motion. So we get mx dot dot my dot dot is equal to this. These are two coupled differential equations. Splitting it separately, dividing by m, we get these two equations. And now I'll divide by g here to make both sides of this equation dimensionless, because this helps keep track of constants. So rather than having to define three constants, for example, we can make it so we only have to define one, and it's a little bit of a trick here. So I divide by g, and I have, I prime these, by the way, so these are new variables. These are related to x and y. They'll give the same shape, but they look like this. And I have minus bg over m, and minus 1 minus this. So this is our dimensionless equation here. And so then I can define capital B as bg over m, and this is proportional to the friction, of course. And we can solve these equations for x prime and y prime, so we get the shape of the curve there. But because they're just linearly proportional to x and y, right, by a factor of g, they give the same shape. So we can just scale it by whatever the real value of gravity is afterwards to get the true trajectory. So I'm going to drop the primes because it gets a little bit messy, but note that when I say x, what I really mean is x over g for now on. So I'm talking in terms of x and y, but I really mean x prime and y prime. So these are two coupled second order differential equations. But of course in Python you can only solve first order differential equations. So there's a trick, of course, that I go through in all my videos about how to do this. When we solve systems of, we have to convert it into a system of first order differential equations. So I define Vx as x dot and Vy as y dot, right? So I'm defining two more variables here. But the trick is that when I do that, I now get four coupled first order ODEs, and you can sort of look at that down here. X dot equals Vx, this is by definition, same with y dot is Vy. But now I have Vx dot, which is really x dot dot is equal to this, and Vy is y dot dot is equal to this. So I have four coupled first order differential equations. And if you've never seen this trick before, it's good to reflect on it and see how clever it is. And it's not something I came up with, but it's something that is so used all the time when doing things like this on a computer. Now, when we solve differential equations in Python, it's always set up in the same way. And it's set up like this. So we define a vector s, and these are the quantities that we want to solve for as a function of time: x, vx, y, and vy. It's a four vector, four differential equations we want to solve. To solve ODEs in Python, before you get into a solver or anything like that, you write a function that takes in s, the vector, so it takes in this vector, and it takes in the time t, and it returns ds dt, the derivative, time derivative of this vector. So that would be dx dt, dvx dt, dy dt. So that's everything on this side of the four equations. So it takes everything on the left side, returns everything on the right-hand side. And so in other words, we want a function f such that ds dt is f of st. This f is just given by the differential equations themselves. And that's what I do here. I define a function f above. It takes in t and s. It also takes in b, so it's an additional argument. We can deal with that in the solver. That's the friction, of course, that I've defined here, b, which is little bg over m, like this. And so it takes in s, and because s is a vector, I extract all the components, and I return this, and all four of these things here are just the four right-hand side of this equation. So dx dt is vx, dvx dt is this, dy dt is vy, and dvy dt is this. So I have this function, and that function is sort of like a puzzle piece that you put into any of the solvers in Python, in SciPy, and it learns to communicate with functions like this. So let me import my packages here and define this function. So now I have ds dt, and I want to solve this for a few different values. So I'm going to define the friction b, the initial velocity v, and a few initial angles. So b is 1, v is 1, and we'll launch it at 40, 45, and 50 degrees. So note that there is, of course, some friction here. And so I can go like this. I'll solve it for a few different angles. Well, let's actually start with b is 0, just to show you what happens with no friction. And so I solve these few things, and I plot the motion, and these are true parabolas with no friction. These are parabolas. That's the solution to the differential equation. And you can see that the thing that travels at 45 degrees, the orange, if you can see the resolution there, it goes the farthest. 45 degrees you can prove is the optimal launch angle for no friction. But as soon as I put friction here, we'll get stuff that happens. So when I solve the differential equation, I use the solve IVP method of SciPy. It takes in this ds dt function that we've solved. I solve it from 0 to 2 seconds. I give it some initial conditions here. So it starts at x equals 0, initial x velocity, y equals 0, initial y velocity. Of course, this is just cosine and sine to get the components of that vector. And I'm solving it over 1,000 points between 0 and 2 seconds, and additional arguments, because I also have the option to give b here. I have to specify it as an additional argument, b. And so I can get these three solutions, of course. So I have all three of my solutions, and now I'm solving it with friction. And so when I plot these now, by the way, looking at the form of these solutions, I can look at solution 1, and it gives a bunch of information. It gives the time points. So these are all the times it's solved for, and it gives sol.y, not to be confused with the y that we solved for. Sol.y is all the solutions to the differential equations. So there are 4 different things. We have x, vx, y, vy, and we have 4 arrays here. So if I take the first component, that gives me my x. Of course, it starts at x equals 0, so that's good. We confirm that. This is vx, y, and vy, and it just comes directly in the order that we defined this function s, x, vx, y, vy. So the way I'm indexing it is exactly in that order. So then I can plot the solution. So here I'm plotting 0, so that's x, and I'm plotting 2, which is y. So 0, index 2, x and y. So I'm plotting the trajectory here. And I plotted at a few different launch angles, and I can look at this, and now you see with friction, it's not truly a parabola. And unlike before where 45 degrees was optimal, you can see the blue, which was launched at 40 degrees, is going just a little bit farther than that orange, and you can barely make that out here. So of course, the next interesting step is to say, well, given an initial launch angle, let's find how far the object goes, and that's what I do in this function here. It's a function called getDistance. It takes in the initial launch angle, it takes in the friction, and the initial velocity, and t is just the time, so 0 to 2 seconds. We have to make sure that the time is long enough so that it actually hits the ground, because if I go t is 0.5, it might only go a little bit up, and the function won't work. So depending on the initial velocity, for example, we have to make sure this is high enough, but 2 seconds is long enough for this case. So I specify my initial x and vy components, just using the angle, and then of course converting it to radians for the function. I solve the differential equation like I did before with the initial velocities and starting at the origin. I solve it for 10,000 times between 0 and, in this case, 2 seconds. Giving the friction as an argument, I set the tolerance really low so that it has to be a very precise solution. And this is where it's a little tricky, and I'll show what I'm doing here above. So I have my solution, right? And I know that y is this one, so that's index 2. And suppose I want to get the place where it crossed the origin, right? So if I look at the sign of this, just like this, my solution 1 above, you can see that 0 means that it's equal to 0, 1 means that it's positive, and -1 means that it's negative. So it goes above, it's positive, and then negative. And it's, of course, crosses the origin when it goes from 1 to -1, so this point here, right? So that's what the sign of this does. So I'll comment this out here for a sec. And then I add another thing. I say, well, I'm going to take the difference. So this takes consecutive differences of that array. So I can look at the differences between this. Again, making sure to put solution 1 here. And I need to make sure my outside bracket. And so the difference is 0 because it's 1, 1, 1, 1, 1, always positive. And then eventually it gets to a point where it's -1, -1. So like the sign would be -1 here and 1 here. And when I take the difference, I get a -2. So this tells me where the crossing position worked. It's a little trick, right? So I can do that. And then finally, what I say is, well, I'm going to say, I want to look at the locations where this is less than 0. So this gives an array of Booleans. And again, I'll put solution 1. And so it says at the 551st index, this is less than 0. So that means that it crossed. And if I want to extract this value, I have to go 0. Okay, it gives it in a little bit of a weird form, so I have to index it twice, and I get 551. That's exactly what I'm doing here. And if I look at this index, so this is 551, and I go sol1.y2. This is just the array. And I look at the 551st index, I can see that it's just positive. 552nd is just negative. So I call that the just above index is 551. The just below index is 552. So that's just that plus 1. And then when I get the x location, I take this index here, so I can then get the x location at this index, which is 551. And 552 is where it's just below, so it's just kind of crossing there. And if I want the place where it intersects the origin, I just take the average of these two. So that's the most complicated function, I would say, of this video. And that's how it works. And again, go through it slowly and really kind of try to understand it. So that's how I get the distance. And I can look at the distance for 45 degrees and 40 degrees here, for this friction and this initial velocity. And you can see now that the 40-degree launch angle actually travels farther. So with friction, you actually want to shoot it at a lower down angle to get it to launch farther. And so what I can do is rather than just looking at 45 and 40 degrees, I can look at a bunch of different angles. Well, let's look at all angles and see what is the best angle in this particular case to launch it the farthest. So I'm going to look at a bunch of different angles between 30 and 60 degrees, and we'll see how far it goes. So it runs pretty quick, and I can plot that here. And so what I have here is the maximum distance it travels, so that's where it hits the ground, and I have the launch angle here. And I'm plotting here the maximum distance traveled as a function of angle. Of course, if I launch it up really high, it's just going to go really short. If I launch it up farther, it'll go a farther distance. Now, with no friction, 45 degrees is the farthest. But with the friction here, b equals 1 and v equals 1, you see that the max is closer to about 41 degrees. So interesting, right? Projectile motion with friction, you want to launch at a lower angle. Now, of course, this launch angle will actually change depending on the friction used in the problem, right? So when there's more friction, it will get smaller and smaller. This is for b equals to 1. So can we find the angle that gives the maximum distance, in this case 41 degrees, as a function of b? Well, that's what we'll do. And it turns out that it also depends on the initial velocity that you send it at, right? For true projectile motion with no friction, it doesn't depend on velocity, but as you'll see with friction, it also depends on velocity. So it depends on the friction. So you have to know what the friction is, you have to know what the velocity is, and then I can tell you what is the optimal launch angle. So we'll look at v equals 1 and v equals 2. These are two things here. And we'll look at a bunch of different angles between 35 to 45 degrees for all these different values of b. So we'll look at 50 different friction values between 0 and 1. And we're going to compare them. So we're going to use these angles to kind of get an idea. And we want to look for the maximum value of all these angles each time. So what I can do is I can vectorize this get distance function. So what the vectorize does is it will create a for loop over get distance, and it'll plug in all these different values of the angles and all the different values of b. And then we'll get a bunch of different results. So, and then we can look at the optimal angles by saying we want the angles for the maximum result, right? So we'll get a bunch of arrays that look like this that we've plotted here. And I want to find the angle that corresponds to the maximum of that array. And that's what I'm doing, the angle that corresponds to the maximum of the array. And so I'll get it for the first velocity and the second velocity. Okay, so it takes about 30 seconds to run. And I'm by no means saying this is the optimal way to do things. It's a little bit slow. And when you're doing sophisticated analyses like this, there's probably faster ways to solve the differential equation, et cetera, using special packages. But this is the easiest way to do it and the simplest way to explain it, such that you can code it up yourself for little problems like this. And so we can plot the results here, and let's interpret the results. So I have different values of capital B, which is equal to bg over m. The units are 1 over seconds squared. And the optimal angle here of launch. So what this says is that, for example, when the friction is 0.4, when you initially launch it at a value of v naught over g, remember that v is v naught over g. Everything is divided by g here. So when capital V is equal to 1 and the units are seconds, then v naught over g is equal to 1 second. And v naught is equal to 9.8 meters per second. And v naught here is about 20 meters per second. And so when I'm launching it at about an initial speed of 20 meters per second, which is the orange curve here, at a friction value of 0.4, the optimal angle that I should kick it at is about 40 degrees here. So that's exactly what this curve tells me. When I'm launching it at 9.8 meters per second, which is the blue curve here, it tells me that, for optimal launch angle is about 43 degrees. So as you kick it faster, and this makes sense, the friction has more of an effect. And so you want to kick it at a lower angle to, negate this friction. And so the obvious question becomes, how does this correspond to regular objects, right? Suppose you're golfing or playing soccer or whatever. What is the friction force here? And what is the velocity that, we typically launch things at? Well, B is equal to 1/2 rho A CD. Rho is the density of air. A is the cross-sectional area of the ball that you're launching. CD is a number inherent to the object that you have to determine. So for a golf ball, M is 0.045 kilograms, this is the radius, and this is CD. From the radius, of course, we can calculate the cross-sectional area just by pi r squared. That's the cross-sectional area of a sphere. Some stats for a soccer ball, and then the density of air. And capital B is just, of course, this formula here, and we plug everything in, and we get this formula. And so I have some sources here for the numbers used in this part here. So I define all the constants I need here, the density of air, gravity, all the stuff for the two balls. and I can plot the results next to what we actually have. And so you'll note that the golf ball and the soccer ball are kind of similar. Now, remember that the orange is 20 meters per second. And 20 meters per second, it turns out, is the speed at which a good soccer player can kick a ball. And you can see that the launch angle is about 43 degrees. Now, for a golf ball, and this is something I challenge you to try and do yourself, is the speed that you hit a golf ball is a lot faster than that. And so there'll probably be another green curve that goes down here. So what I challenge to the viewers of the video is to look up the speed of the golf ball, solve for a solution here and say, well, what's the optimal angle that you can launch a golf ball at? Because you're hitting it a lot faster. So friction has a lot more of an effect on it, of course. But you can see that for these objects, right, rather than kicking it at 45 degrees, for example, with the soccer ball, and orange is like about the speeds that you'll kick it at, you actually want to kick it at 43 degrees. And now, I'm not sure that soccer players are really thinking about this in terms of launching it as far as possible. I don't know if their kicks are necessarily that precise. But I have a feeling for golf, where people are designing club faces and things like this, that this optimal angle really matters for getting the maximum distance possible. And so this is an interesting side project that you can take from this video and sort of play with yourself and see what happens. Anyways, thanks for watching this video, guys. If you enjoyed it, please be sure to like and subscribe. All the code is on GitHub. There's a link in the description to that. Reminder to join the Discord server as well, which I also have in the description. And I'll see you next time.